It's not too clear. String players out there, has your teacher ever told you to play closer to the bridge to get clearer harmonics? Ever wondered why? Also, maybe you're familiar with the technique ponticello. Instead of playing at your normal contact, you play really close to the bridge. And it's all like whistly with all those overtones. So why does that happen? Well, I'm square root of -1, and I've just spent a little time working through the math behind why playing closer to the bridge gives you both better harmonics and can also create that ponticello sound. This video is inspired by a homework problem, so thanks to my physics professor for giving us that and that food for thought, which has been really fun to work with. We're going to take it a little step further today and look at the harmonic content depending on how close to the end of the string you're playing, and see if we can represent that both mathematically and graphically. So it should be fun. So first, let's remember what harmonics even are. We have here a string of fixed length, and the two ends of it are fixed, so they're not going to move. So we're going to form a standing wave on this string such that those two ends remain fixed. Well, the simplest way to do that is just to have a half a wavelength exist on the string, so you have just one curve to the whole thing. But you can also have a wave such that the very middle of the string remains fixed, and then you have a full wavelength or two curves to your wave, your standing wave. In reality, these two waves exist simultaneously, forming a complex wave, as do standing waves with 3 half wavelengths, 2 wavelengths, 5 half wavelengths, and so on, for all multiples of a half a wavelength going up. They all exist to diminishingly small degrees. Each point where the string stays still, i.e. the standing wave drawn, intersects the line of the original string, is called a node. The only two fixed nodes for a just plain long string with two fixed ends are the two ends of the string. But we have all of these other nodes that exist for different harmonics. You can change which harmonics are more prominent by changing which places along the string tend to be antinodes. So when you pluck at exactly halfway along the string, you're making that midpoint more likely to be an antinode, and therefore you're making that first harmonic more prominent. Meanwhile, if you were to pluck instead at, say, 3/4 from one side and 1/4 from the other, then you'd have different harmonics that are more prominent based on which ones have standing waves with a higher amplitude at that point along the string. So what we're going to do is mathematically prove that statement that we just made, and in the process examine the harmonic content of the string when pulled at different points. So let's start by looking at the relative amplitudes of the first few harmonics when you pluck at halfway along the string. We have our initial conditions, so this is just amplitude as a function of distance along the string at time equals 0, so right before releasing the string. And so you can see for A just being an arbitrary constant, we just have slopes going up to the center and then an opposite slope going back down to the other end. That's all that this is saying here. This will give us our linear wave equation, and so we produce a standing wave with amplitude 2 over L times the integral for the length of the string. Initial conditions times sine knx, where kn is the wave number and pi over L, and n just describes which harmonic we're talking about. So if we evaluate this, we'll get an expression for amplitude, relative amplitude, in terms of n. And we can plug in different n's for the different harmonics and see the relative amplitude of the different harmonics. So let's plug in the values we have for the halfway pluck. Because our initial conditions are piecewise, we need to break this up into two different integrals. So this integral on the left is the condition for x less than L halves, and this integral on the right is for x greater than L halves, although we're going to have to break it up again because we still need to multiply out this 1 minus x over L term. And we've changed our bounds of integration to go from 0 to L halves and L halves to L. So let's clean this up a little bit. As I said, we can split it into three different integrals now. We can also pull out some constants to the front. So let's pull out the 4a over L squared. Notice that because the middle integral did not actually have an L in the denominator, since we can't take an L out of the denominator because there isn't one, we're going to multiply by L to make sure that this all factors properly. Skim over the rest of that, it's all straightforward. And now we can integrate each of these separate sections, these three separate sections that we have, and we're going to need this identity. The integral of x sine ax is equal to 1 over a squared times sine ax minus ax cosine ax. So using that to evaluate this first integral here, we have kn instead of a, and our bounds of integration are from 0 to L halves. So when we plug those in, we get both of the 0 terms going to 0 because sine of 0 is 0, and the cosine term is just multiplied by 0 at front. So those are both 0, and so we just have 1 over kn squared times sine kn L over 2 minus kn L over 2 cosine kn L over 2. On the middle integral, we don't even need that identity. It's nice and simple. We can just do a little chain rule, or I guess it's not called that since it's an integral, but the reverse of the chain rule, I suppose. And you're pulling at that 1 over kn to the front, and integral of sine is negative cosine, so we're actually going to flip the order of these terms because they're both negative, and have 1 over L over kn times cosine kn L over 2 minus cosine kn L. And then for this third integral, we're doing it just like the first one, except because we don't have a 0, we're keeping each of those terms in there, each of the L halves terms and each of the L terms. So we come up with 1 over kn squared sine kn L minus kn L cos kn L, and then these next ones would be subtracted, so we're just going to flip the signs. So minus sine kn L over 2 plus kn L over 2 cosine kn L over 2. So now we need to put those all together. Again, I'm going to pull out another 1 over kn squared, and again the middle term only has one kn in the denominator, so we're going to need to multiply by kn and have that kn staying in there. And now let's see how many we have of each of the different terms. Let's look at the sine kn L over 2 term. We actually have 2 of those, so that's 2 sine kn L over 2. And then our cosine kn L over 2 terms, we have kn L over 2 minus kn L over 2 plus kn L of them, so that works out to 0. And then we have minus and plus of kn L cosines of kn L, so those work out to 0. And then what do we have left? We have a sine kn L left. But you'll remember that k sub n equals n pi over L. So this sine kn is always going to be a multiple of pi, which if you think about your sine function is always going to work out to 0. So really we don't need that term in there either. So now we just simplify this out and we only have the one term, which is 8a over L squared kn squared sine kn L over 2. And now if we plug in the value for kn, our L's will cancel out, and we have 8a over n squared pi squared sine n pi over 2. So let's see what that works out for the first few values of n. So we get the amplitude of the first harmonic is 8a over pi squared. The second one is actually 0. The third one is negative 8a over 9 pi squared. This negative just means that it's out of phase with, say, that first harmonic. So at this point it might be down or, to the left, where the other one's to the right or whatever. And then we could keep going. All even values of n would of course give us sine equals 0 and therefore a 0 amplitude. So is that realistic? Well, I mean, Probably you're not going to have an outright 0 amplitude for them, but it's going to be super low. And you have to remember the timbre of an instrument is also not just from the string vibrating, it's from all of the other elements of the instrument and room around it and the person playing vibrating. So yes, there are going to be other harmonics present here, but this is what we're talking about as the primary things that are existing in the sound from that string. So let's now go to where you're plucking a quarter from the end of one string and 3/4 of the way from the other end. And so let's revise our initial conditions. The slopes up and down are no longer going to be the same because you're taking much longer along the string to get one way than the other. And convince yourself of this if you need to, but basically the slope one way is 1/3 of the slope going the other way. We're keeping the 4 in, pretending like you're still pulling the string out to the same distance before plucking, but really it doesn't matter because our A is arbitrary. We're just talking about the relative amplitudes anyway. We're just trying to see some patterns. So now we plug it into the same formula. We just have different initial conditions and we have different bounds of integration going from 0 to 3/4 L and from 3/4 to L. This time let's pull out an 8a over 3L squared, and we'll notice on the next two terms we don't have 1L and just 1, we have 3L and 3 due to having that one slope that's 1/3 of the other. And now I'm going to skim over this integration because it's all the same as it was before. The only difference is the bounds of integration and the constants that you're carrying through it. So, and we still have zeros in the same places, so none of that's different. We'll still have all the same terms. So again, we can put them together still just with different constants out front, and again, we can ignore that K and L term because it will always be 0, so I'm not even going to write it here. And we'll plug in the value of Kn, and let's put in different values of N, and we get, for N equals 1, we get 16 squared of 2a over 3 pi squared, then we get negative 32a over 12 pi squared, we get 16 square root of 2a over 27 pi squared, again, a4 equals 0, for N equals 5, you get negative 16 square root of 2a over 75 pi squared. Again, we're just looking at that opposite phase. And then for N equals 6, last one, let's just say, and this is 32a over 108 pi squared. So what's our pattern here? What's happening? Well, what's happening is we have two things dependent on N that are shaping this. We have an N squared in the denominator, which is just making each sequential harmonic less and less prominent. They just get smaller quadratically, right? Because N is squared there. And then the other thing we have is what checks if our plucking spot is actually in phase with that given harmonic. This little sine figure here, obviously when sine is 0, that harmonic is nominally at 0 amplitude. And then sine would be maximized if that plucking point was a high point on the standing wave corresponding to that harmonic. So we just fluctuate around that as we just get smaller and smaller. So we looked at 1/2, 1/4. Let's just look at the general case of plucking that string at 1 over p from one end, and therefore p minus 1 over p from the other end. So how can we generalize the initial condition? Well, the shallower side of slope is spread out over p minus 1 portions because the last portion is for the steep slope part. So if we're still assuming we get to the same point of max amplitude where you're holding the string to pluck it, then you'd get this pa over p minus 1 times x over l for the less than p minus 1 over p l's. And then the other way, on the other side, you'd have the steep version, pa times 1 minus x over l, just like we had before for x greater than p minus 1 over p l's. Again, we can just plug that into our equation just as before, and our bounds of integration look a bit funky, but that's what they are. Still just the breakup of this piecewise function here. You'll be able to pull out 2pa over p minus 1 l squared to the front, which just like in our previous example, we'll leave the second two terms with a p minus 1 in front of them. Oh, and there should be an L on the middle one too, because that L wasn't in the denominator. So again, this isn't really more complicated. It really just perfectly matches what we've done on each of the previous cases. And again, we can ignore some of those. I'm not going to show all of the integration. We can ignore some of those terms that cancel out, and you'll be left with just the sine kn p1 over pl term, and then the sine knl term, which will go to 0 in every case. And so here we have a general formula for the amplitude, giving which harmonic you're talking about and given where we want to pluck it from. And you'll notice that if you plug in p values, this completely matches the a sub n's for our previous two cases. Now that we have that general formula, we have the information we need to make a graph, and this is just Desmos online, free software. And what we're going to do is graph the relative amplitudes versus n. So this is not representing the amplitudes along the string, but rather the relative amplitudes of higher and higher harmonics going up. In our xy coordinate, y is just corresponding to amplitude and x is just corresponding to n, so we'll just change the n's to x when we type them into Desmos. I'm also just going to multiply all of these by 10 just to make it easier to see on the graph. Again, a was just arbitrary, so this is fine. So for p is 2, again, that was where you were plucking at half a string. We have 2p squared, so that's 8 over 2 minus 1 is just 1, so this will just be x squared pi squared. And then we need the sine portion, so it's sine of n pi, and then 2 minus 1 is just 1 over 2. And sorry, I forgot I need to change that n to x as well. And so we get this graph, and again, I'm just going to say this is not accurate because n values are discrete, and we're watching this as a continuous graph, but it can still show you more clearly than just a few dots what the trend is in this amplitude versus n. And so you can see that it tapers off really quickly, and yes, it's still periodic to whether or not that lines up with the spot that you're plucking and the peak of the standing wave, but it's still really, really small after that first harmonic. So now let's just take this and make the next line up. Instead of 2 times 2 squared, we have 2 times 3 squared, 2 times 9, which is 18. And now instead of 1, we have 2 on the bottom. Instead of 1, this is 2, this is 3. And so what you can see is that we lose that first harmonic faster, and so that we get higher amplitudes for the progressively higher harmonics. So let's keep going up. Let's see. 4 squared is 16 times 2 is 32. So again, we have even higher amplitudes. You can see this. Let's do another one. 25, so 50. You're getting even higher. And then let's skip. So let's say you were going to play right next to the bridge. So it would be like ponticello sounding. Okay, so let's make it be 1/100th of the distance away from the bridge. So this is really pretty much ponticello. And let's see, 100 squared, so we're looking at 20,000. Here we go. And for 99, and these. So here you go, you have these really high amplitudes for higher harmonics, and this is how, when you play sul ponticello, you can get all of those overtones to still sound even though you still have the fundamental frequency open, and that is why you get that ponticello sound. Let's zoom out even further. Right, so you can get the higher ones, and even out here you can still see the wiggle, which is not true for when you're plucking closer to the middle of the string. So again, that just means that there's more of the higher harmonics relative to lower ones the closer you're playing to the bridge. And as I said, this is how you get that sul ponticello sound, and it's also why it makes sense to play harmonics by being closer to the bridge, and that's why they sound clearer, by causing that region next to the bridge to be more of an anti-note than it would have been. And so this is cool. We can now visually and mathematically see why that makes sense and see what the graphs looks like, and we've proved it ourselves. This is pretty great. And definitely not something I've fully understood in music lessons before either. Hey, thanks for watching. This was super fun. If you want to explore more cool physics and math and just general science about the world around you, definitely subscribe. Also, liking this video and sharing it with your friends will help me out a little bit. Until then, have some fun, happy math, and happy practicing. Meh. Oh, by the way, in a couple days, I'm going to do a more general video about the physics behind string instruments, so definitely check back for that. See you then. Bye.